Well, let's see. I'm going to put them in those links into a document, um, and I'll put them on the Google Drive. Um, you can view them. We're going to go over the really important stuff right now, and the stuff that I kind of want to focus on. All those videos are great information, as we've said before. Um, great sources of information. But we're going to kind of focus the discussion on certain aspects. So let's see. All right. So one of the videos, I don't know which order everybody watched them in, so I'm just going to kind of jump around from subject to subject here. So one of the videos we talked about fog, and we described fog. So why is fog really important for us to understand and be able to predict?
For visibility?
Yeah, definitely.
Yeah, your minimums. You won't make your minimums.
Yeah, it's pretty. When fog rolls in, we lose that visibility really quick. When it's a cloud layer moving through, our cloud layers don't tend to completely prohibit us from being able to conduct our operations, because typically it's a good 400 or 500 feet off the surface at least. But when the clouds start to descend lower and we start getting into fog issues, then basically it completely eliminates the legality of the airport. We no longer have minimums at the airport, and so it can be really detrimental to the operations of an airline. Some of the areas of the United States that we get a lot of fog on a regular basis, like LA and San Francisco. Seattle gets it too, but we'll go over the different types of fog here. I want you guys to basically take notes as to how that type of fog is created. So as we go through these, I'm just going to talk about them, but I want you guys to really focus your note taking on how that fog is created. So, so we'll go through this here. So, mist and fog are the terms used to describe low visibility caused by water droplets suspended in the air. Mist is a term used to describe visibility of greater than 1 kilometer, while fog is a term used when visibility is less than 1 kilometer. Fog is effectively surface cloud that has significant impact on conduct of flying operation, particularly landing and takeoff. So that just kind of reiterates what we have just talked about. So radiation fog typically is created. You can see it right here and take notes, but it's just created when there's that clear, just really calm night. And basically what happens is the surface of the Earth's surface loses heat. Loses that solar heat, solar radiation, and cools. And then the moist air comes in contact with the cooling surface and also cools to the temperature. And when it falls below that dew point, that's when the air fog forms. So when we see this radiation fog, it's, as it says down here in this anticipating radiation fog, It tends to be on nights where there's clear skies, moist air, and light wind. Radiation fog, as we tend to see, clear up rather quickly when the sun comes out. It's kind of interesting to see how um, when the sun comes up across the country, when we're watching it on our weather um, our weather software at work, you can watch these areas, these certain areas like Houston, San Francisco, LA, just to name a couple of them. But what happens is um, there will be kind of low visibility, it'll be down at like 2 miles or something like that. And then right before the sun hits them, about that 20 minutes before the sun hits those areas, the fog intensifies and our visibility just drops out the bottom. And it's not even forecast at the time. Um, but yeah, so like I said, it tends to happen on those clear nights, those clear, cool nights. Well, as soon as the sun hits the surface, it kind of intensifies a little bit more. And then after about 30 minutes, all of a sudden the visibility is back up. So you'll see these temporary TAFs and METARs, or amended TAFs and temporary METARs come up. And basically you can see just that weather just drop. The visibility just drop at the surface. And then it's almost like clockwork. As soon as that sun generates enough of that solar radiation and the surface warms up enough, it dissipates. Kind of think of it as like going into taking a shower. Your mirror's nice and cool. Well, then it has that warm, moist air hit it, and it fogs up that mirror really fast. But as soon as the temperature regulates again inside the bathroom, all of a sudden that fog clears. So that's our radiation fog. The other type of fog that we see is advection fog. So this is similar to radiation fog, but advection fog occurs when warm, moist air mass flows over across a colder surface. The air mass is cooled from below the colder surface, and and if the temperature in the air mass reduced to the dew point, then the fog forms. So when we see advection fog, it's more of that circulating air. So it's formed similar to radiation fog, but what's happening is the air is moving rapidly across that cool surface, and it's cooling that moisture in the air rapidly. It says here that's the big difference between advection fog and radiation fog. Sorry. So advection fog. The difference between advection fog and radiation fog is, like I said, it changes. The radiation fog is formed from a warm surface, whereas the advection fog is formed from a cold surface. But then the air type basically is the same. The difference between the two is that wind is associated with advection fog. And you can see when it talks about strength to a gale force wind, that's a pretty high speed, and so yeah. Does anybody have any questions on those so far?
Yeah, so did you say that radiation fog is formed from cold wind or warm wind? I forgot.
All right. So another type of fog that we see is the frontal fog and hill fog. Let's see. So
Hey,
this,
Garrett, you hear us? Garrett.
we don't call it hill fog, uh, but um, we call it upslope fog. So
Garrett, can you hear us?
right downhill fog, right upslope. So what happens with this frontal fog or the upslope fog is when like it says here, when during the passage of a front, a cloud extends down to the surface. And this is especially the case over higher ground and may also be termed hill fog. So we talked about like um, valley winds and mountain winds and stuff like that yesterday. Well, what happens is those clouds just the temperature and everything drops and no, I can't hear anybody.
Can you hear me?
Can you hear us?
Here, hold on. Let's see.
Yes. So my question was, what were the two differences again? I know that radiation fog was formed. I don't know if it was formed with cold or warm wind again.
Yeah, so radiation fog, going back up here. So radiation fog is when that, like it says here, the land is cool and the moist air comes in contact, cooling the surface further.
Well, I got that part, but just the differences between radiation and
Okay.
the other fog.
So land, the difference between radiation fog and advection fog is the surface of the Earth is already cool with radiation fog. So it's that cool surface, and then the moist air hits that cool surface, cooling it further and lowering the dew point to where the moisture turns into fog. Advection fog is when it's warm land, not cold land, but warm land, and moist air mass flows across the surface. So, oh, sorry. Oh my gosh, I read that wrong.
Yeah, it's kind of a long definition. I'm trying to summarize or shorten up the difference between the two.
Shorten it up the way
Just,
that makes sense to you. I don't know how to.
Yeah.
Just the basic thing is I'm trying to. Okay.
I got it down now. I'm trying to erase a bunch of stuff and kind of summarize it a little bit.
Yeah. So radiation fog is a cool surface, and then the moisture comes in contact. The moist air comes in contact with the cool surface, cooling it further.
Garrett?
Yeah.
The video said for radiation fog, ground cools and air cools reaching dew point.
Right.
And then for advection fog, caused by advection of moist air over a cold surface. And I don't know if that was like water. I don't know if they showed a bridge or.
Oh, okay. So yeah, that's where I keep mixing it up. It's the heat, where the heat is, because there has to be one of them's going to be warmer and one of them's going to be colder. With advection fog, the air is warm and moist, and it flows across a cold surface. The main difference between the two is that radiation fog, there's no wind or a very light wind associated with radiation fog. Advection fog, there's typically a high speed wind associated with it. Did you get that, Matt?
Yeah, I'm writing the rest of it down.
All right, we can wait for just a second.
Only one that wasn't able to watch the videos because none of the links worked for me. I tried like typing it in.
Yeah, so Greg said that he's had a couple problems with that. He said the way he's been able to fix it is he just copies the link from the chat and then opens up an internet browser and does it. For some reason, I don't know what's happening, but the links are valid links. I double checked them. But what I'm going to do is I'm going to post them on a Google Doc and I'm going to put them on today's Google file.
Okay, and then I'll just watch it later. Okay, thank you.
Yeah, I'm really sorry about that.
No worries.
Yeah.
I got it all down now, so I'm good.
Okay.
Thanks.
So, all right. So those are the two main differences: is wind, no wind, right? And with advection fog, it's warm air over a cold surface. When we talk about frontal fog and hill fog, so as we said before, basically, as a front passes, the cloud extends down to the surface. And as it moves over higher ground, it's not hill fog, it's called upslope fog. So make sure that you change that. You can just go ahead and write this down, but change hill to upslope fog. That's how we term it now. So when air in contact with the surface becomes saturated by evaporation from the rain that has fallen, these conditions may occur in cold air ahead of a warm front. In the cold air ahead of a warm front. So, does that make sense to everybody?
This is the kind that you can always like see over like Pine Valley.
Yeah, that's upslope fog.
Like when it looks like just when it looks like the clouds are like just descending down the side of the mountain all the way.
Yeah, it
down
tends to be reverse of that though. So upslope fog tends to move up the hillside and then dissipate over.
Oh no,
the top
I'm just
of the
saying.
hill.
I'm just saying it looks like the clouds have just like fallen down the side of the mountain.
Yeah. So they'll descend. The clouds will kind of descend down in the valley, and then just climb up the hillside. Yeah, that's a perfect example
It's super
of
pretty.
upslope fog. Yeah.
In the Texas prairies, at certain times of the year, every single morning, the fog would do that, and the deer would follow it and stay right on the edge to be kind of protected.
Yeah.
So they would kind of
So
keep walking
pretty.
along and follow up the hills, and it would just be amazing. Every single morning it would do that.
Huh.
So it was really cool how to just kind of go uphill, It's really interesting.
Yeah, it's incredible to watch. I love just watching, especially in Salt Lake. It's almost like from a movie, It's just really pretty. Just mountainside just gets uncovered by. It's just like this unveiling of the mountainside, It's really pretty. Especially when you get that virga and stuff. So the virga is that really wispy cloud. It looks like the cloud just kind of like falling out the bottom. I don't know how to explain it. I don't know how to spell it either. Whoa, that's not. Nope. Gosh. That was not intended. How do you spell virga? Virga. Hopefully I don't get something. There we go. Something unexpected again. That was horrible. I'm really sorry about that. So this is virga. That's super embarrassing.
Yeah, where it looks like the clouds are disintegrating.
Yeah. So basically what this virga is rain falling and evaporating before it hits the surface. So, but yeah, that's virga, not verga.
I love when you can see that.
So, yeah. So what's really cool is watching it, in the Salt Lake Valley when you have that virga, and then you see the upslope fog as well. That's pretty amazing. But so the other type of fog we tend to see and are concerned with aviation is steam fog. Now, steam fog is basically just the reversal of advection fog, or not advection fog, but radiation fog. So steam fog is when that cold air flows across that relatively warm water, and the water vapor evaporating from the surface of the water rapidly cools below its dew point and is mixed with and cooled by the cold air. So you see this across lakes in the morning and stuff like that. This doesn't tend to be as big of a problem because what happens is once the water hits the land around it, it dissipates pretty quickly. Because like it says, what's happening is the water's actually evaporating off the lake. Because it's warm, it's just getting cooled rapidly as it evaporates off the lake. So when it goes over land, there's no more of that evaporation, and so it dissipates rather quickly. So you can just see a little bit more of what it is. So yeah. So what are the effects of fog? Low visibility, right? It's as we said before, it can really change operations quickly. Just what was it, yesterday? Yeah, yesterday Chicago and Detroit just tanked bad, and a lot of that was due to fog and low visibility. So
yesterday was the same thing at the St. George Airport. I mean, for like a good 3 or 4 hours, it was really foggy around the mountain areas around the airport, and the airport was just dead of traffic. There was no traffic coming in.
Yeah, so I caught a flight on Wednesday night out of St. George. Let's see if I got the picture still. Excuse me. So this is my flight when it was coming into St. George. I took this screenshot. I was watching it on FlightAware. The pilot came in, and right as she got to about right here, as you can see, the visibility just tanked bad at St. George. There's a lot of low-level clouds, and then like the fog just rolled in it only lasted for like 20 minutes or so, just enough time for her to come in and do another approach on the airport. But yeah, she right as she started her descent, it's like the visibility just started dropping and rain started raining, and then as soon as she turned to do her go around, the fog was lifting and the ceilings, rose really quick. So that's what we call a missed approach. If you guys were ever wondering what it looks like on radar. Yeah.
Wouldn't it be a missed approach if she went past the airport and then around, or?
No, not necessarily. So a missed approach is basically just whenever the pilot decides that this landing is no longer safe. So they'll call a missed approach. They'll be coming in. They can't see the lights. The visibility's too low. And they just don't feel like the safing. And what another thing that can cause a missed approach would be things like crosswinds, turbulence. It's been really turbulent at St. George, coming in and out of St. George over the last week.
I flew into Yellowstone about 2 years ago on a SkyWest flight, and I had the privilege of being on jump seat. And as we started the approach down, he did a missed approach because there were elk that meandered right onto the runway.
Oh, that's awesome!
So he had to call the flight the flight service station, I think, and ask them to go out there and throw rocks at them and get them off the runway. So sure enough, you could see as we banked around, a bunch of the ground guys come out and throwing rocks at them, and they all took off into the hills, and then we were able to land. It was hilarious.
That's awesome. Yeah. That happens a lot at airports where you'll be coming in on an approach and the fuel truck will drive across the runway or something. You got to go missed, but that's pretty awesome to see, like in Yellowstone, watching the animals take the runway, A lot of times what they'll do, like for birds and for wildlife like elk and deer and stuff, is they'll take little firecrackers, M80s, and they'll just throw them at them, spook them, but get them out of there. But yeah, I can hear you.
Oh, okay, my mic wasn't working. I was going to tell you earlier, working in Medford with the fog, one of the biggest problems we had, because San Francisco was one of our main flights. People would go to San Francisco to catch a plane somewhere else. There were so many times that blue skies in Medford, and we'd had to cancel the flight, and people were furious. We had to tell them, there's too much fog in San Francisco. There was one lady that her son had to get to college football tryouts or whatever, and he had to be there the next day, and it was in the Midwest somewhere, and all the girl that was working the computer was like, I'm really sorry. So she had to rent a car, and they can't get to San Francisco in time to catch their next flight. So it totally messes up their whole schedule.
Yeah. It messes with us pretty bad. And it's kind of funny. I guess not funny so much, but let me pull this up really quick. But so I'm going to digress a little bit here. But what happens is the weather forecasts are published. It's almost like it's the new guy's job to forecast the weather. It's crazy. I don't know. It just seems like the TAFs are only so accurate. And let's see. I'm trying to pull up forget it that way. But
there's another chart that we use a lot that kind of like, how do I say this? It basically says, well, this is how confident we are that the guy writing the TAF is doing his job right. Let me see if I can find the chart.
Like a percentage of confidence or something?
Yeah, it's funny because it's all put out by the National Weather Service, right? But yeah, they let me see if I can find it. It's just kind of hard to find it at work. It's just a bookmark for me. But yeah, they just basically say this is the forecast, but this is our confidence that we actually forecasted correctly. And they contradict each other all the time. There it is. Found it. Let me show you guys.
Hey, Garrett, I don't think we're seeing anything on your screen. Oh, never mind. I see it.
Yeah, I was just trying to find it without having you guys see all the different mess that I was making trying to find it. So, anyways, this is called our aviation forecast discussion. And when we go in here in the morning to San Francisco and stuff like that, we can have a TAF that's saying 6 statute miles of visibility and skies clear. But then you'll come into this aviation forecast discussion and it'll say, yeah, we have little confidence in the forecast. We believe that fog will roll in at this time. And it completely contradicts the TAF, but it's the same service that's generating these reports. So this is also kind of used. They also get the information for this from the actual weather observers and the different stations in the area that have a little more actual knowledge. It's like government work, you know. You'll have an office in DC calling the shots, saying this is what the TAF's going to be, and they're just pumping out TAFs all day long. But then you have the guys that actually do the weather observations in that area, and they're like, yeah, not so much. That's not really what's going to happen today. So it's just
that's funny. Kind of like you got 10% chance of rain, and I'm standing there to getting soaked, you know?
Yeah.
So it's pretty irrelevant to the guy who's getting rained on.
Right. Yeah, and you can look through any of these different areas, and they'll tell you, you know, let's see if we can find something. Yeah, I'm just looking for something that says little confidence in the TAF or see. I'm guessing the TAF said that there was going to be low visibility over Los Angeles not long ago, and they're just kind of like, yeah, it never happened. And then they say, well, we've got high confidence in the CAVI test with minimal wind issues. So basically going forward, and then we've got good confidence in this TAF. So, but then there's those ones that are just like, yeah, it's not going to go down like that. Denver's notorious for putting out very contradicting information on their weather. But the point I'm trying to make here is that you got to be careful when you're looking at these forecasts. Yes, we are bound by the TAF for legality, the METAR and the TAF for legality reasons, but does that always mean that it's the right decision sending a flight into an area just because the TAF says that it's good? What will happen is Medford will be 10 and clear, like you're saying, but then San Francisco is just garbage. And the TAF will still read for San Francisco, 4, 5, 6 plus miles of clear and no ceilings, or scattered clouds at 4,500 or something like that. And next, you send the flight with no alternate, no extra fuel, because you're like, well, the TAF says that the weather's good. Next thing you know, there's an amended TAF or another weather report that comes out while your plane's in flight that says that they're at an 8th mile of visibility, and there's no way they're getting in there. You just see planes all of a sudden start diverting. So you've got to be really careful when you're forecasting this weather, because things can change so rapidly.
So with an airport like San Francisco like that, would you ever say, well, I know the weather can change in 2 hours.
Yeah.
So add extra fuel and an alternate just in case?
Yep, definitely. We do that on a regular basis. Just today, we had a flight that, or I had a flight that it was going into Seattle. I'll just show you Seattle's weather right now. Let's go to WSI really quick. This right here this morning looked a little more like this. But Seattle was still legal. They had ceilings at I want to say they were at 2,500. But because of the wind shift and everything, we were just like, well, that could drop pretty quickly. And then if the wind shift, then their ability to bring aircraft is going to be reduced, because if the wind shifts, then they can only land so many per hour. So there's just this general knowledge of, Seattle, when the conditions are like this, we're just going to add an extra 15 minutes of fuel so that the pilot, if he needs to, can make a decision to get out of Seattle, go down to Portland, or to, and get out of that weather situation if he needs to. But the TAF was completely legal. Another thing that happened today, my brother actually, he dispatched a flight, and it was the first diversion of the day, but he dispatched a flight that was going from, where was it, Denver to Pueblo? I know it was going into Pueblo. No, it wasn't from Denver. Anyways, it was going into Pueblo, Colorado, and all of the conditions, there had been absolutely no precipitation all night long. There had been absolutely no report of any weather whatsoever. The weather report said that it was 10 and clear and everything like that. So 100% legal to dispatch. Well, 10 minutes before the flight got there, a NOTAM was issued that said the field conditions dropped to basically poor braking action, that there was ice on the runway basically, and it was really hard to stop. And the pilot was like, I don't feel comfortable with it. We're going to Denver. And, that's just how things can change from what seems to be completely legal, completely normal, like not a problem in the world, to, okay, we've got a problem. We've got to, we've got to kind of go with your gut instinct at the same time. And nobody, if you are adding fuel or adding an alternate because of your experience of certain airports or seeing certain patterns at airports or with weather or with traffic, if you decide that I just don't feel good about sending this flight with absolutely no backup, and you put an alternate and fuel on there and just notate the release saying, hey, I just don't feel good about it. It's just there in case the pilot needs it. Nobody's ever going to question you on that. Because that is your job as a dispatcher. You and the pilot in command are solely responsible for the lives of the people on board and for the safety of that flight. So you can't really get questioned on that. Does that make sense?
Oh, yeah.
So there's several times where you get that gut instinct. And what's crazy is that 9 times out of 10, your gut instinct tends to pan out. My brother, he had the 2 a.m. shift during the summer last year. Denver would be reporting clear, but then every morning the same time, he had the same flight every morning going into Denver. I think it was from Houston to Denver, and it would get like, so where my cursor is basically where Denver is, right? They have what are called gates around the airport, and what would happen was every morning, unforecasted, there would be a thunderstorm that would pop up, closing off 2 of these gates. Well, his flight's coming in from the south, and so to get around the storm, his flight would have to come way down here, way out of the way, and then come back into Denver. So my brother, after a day or 2 of seeing the same thunderstorm pop up consistently at the same time, he told the captain, he's like, look, it's going to happen. It's been consistent. And the captain's like, yeah, I agree. They threw on 15 minutes of extra fuel to help him make that cut. And my brother actually, as soon as he'd see the clouds start popping up here, he'd be like, all right, reroute this direction. And every time it panned out to where that gut instinct and that tribal knowledge that you kind of get panned out for him, and basically saved the pilot a lot of work, a lot of stress trying to get into Denver. So,
Garrett, I know that flight crews bid by the month, so they can get that tribal knowledge. Do they also do the same in the kind of a regional bid structure for the dispatcher, so they can kind of gain that repetitive view of an area?
No. Not with SkyWest. Now, if you're going to Delta or a major, they'll separate it, flag and domestic. So there will be certain people that only do international flights, and then there's certain people that only do domestic flights. But at SkyWest,
so you may just get 15 random flights, different every day, different directions.
Yeah. Today, for example, I had flights, Salt Lake to Boise. I had like 2 flights going into Phoenix, 3 flights going to LA from various points. I had flights going into O'Hare, Detroit, Cleveland, Minneapolis. It's just all over the place. But what's crazy is that you get a basic understanding of where the problems are. And we also, at SkyWest, you've got your hubs, depending on the air carrier. Your main hubs, you know what happens at the main hubs every day. And, you also get reports from air traffic control to help us get that overview and understand what's going on in the airspace any given day. There is a different desk. We have 2 desks dedicated to mountain ops. That's what we call it. Mountain ops are like Aspen, Mammoth, Butte, Montana, just some of these high altitude, we call them SAT-4 airports. So they have extra special requirements for us flying into them because of how dangerous it is to fly into them. Like SkyWest has kind of made the Aspen flight our bread and butter. We definitely conduct the most flights out of any airline into Aspen, and so we're kind of the resident experts. Air traffic control actually will, during their briefs, they'll actually ask the SkyWest representative about conditions in Aspen and things to look out for, just because of how often we work those Aspen flights during the winter especially. But yeah, we've got a desk that's dedicated just to those flights because of how intensive the workload is due to the special requirements. You can't mess those up, They're very special airports. They get crazy winds, they get runway contamination, they're extremely high altitudes, so performance is horrible, so.
Well, I would imagine if you're looking at a map like this,
mm-hmm.
every day on your shift, you're going to see kind of what develops every day
mm-hmm.
during that time or every night, whatever it is. So I imagine, like your brother, you get pretty savvy of the Dallas area or the San Francisco area of what's happening during your shift.
Yeah, and definitely this is similar to the view that we have on the program we use. It's called Fusion. The only difference is that Fusion also will bring in all of our PIREPs, our AirMets, SIGMETs, NOTAMs. We can look at routes and everything. We can look at every single aircraft in the sky at any given point in time. But the basic overlay is this kind of picture of the country, and we can see these radar signatures, see the cloud tops, and the areas of concern. So you get an understanding of how the weather kind of moves about the country. So, and you have certain airports that you're like, it's always perfect there. It's the perfect alternate, but then you have airports that every time you see them.
You were talking about that jet stream, and you can see where that weather formation just striping right through all that green right across the jet stream.
Yeah. Just you get to that point where you have a basic understanding of how the jet stream's flowing through the country. You get an understanding of where the highs and the lows are just looking at maps like this. And so pretty interesting stuff. Like, it keeps you on your toes and really helps you appreciate the day-to-day operations, SkyWest, we not only are we having to do that, we have a pretty high workload every day too. A lot of the dispatchers have anywhere from 50 to 60 flights on their desk every day during their 10-hour shift, and so it's a lot of work. And you really got to be paying attention. So, but yeah, that pretty much covers the fog. Why don't we take a 10-minute break, and then we'll come back and we'll talk about adiabatic lapse rate. So, sorry. All right, Yvonne.
Yes.
Yes, we are.
Yes, I am. Okay, that's what I was wondering. And I know that Marissa has which equations? There are equations that are in the video that she hasn't watched yet.
So it's we're going to talk about the standard adiabatic lapse rate, or basically we're going to talk about how this all affects us.
Okay, I'm scared.
No, so we're going to keep it really simple. Yes, there's a dry adiabatic lapse rate, and there's a moist, and there's all these different types of, you've got the Dowler and the Saller and the just all this garbage. Not all of that applies to us as dispatchers. We're going to talk about what's important. The video explains all the rest of it. We're going to talk about the one that we use in equating our flight plans.
Reminds me of my high school physics class with the balloon, releasing the balloon at the top of this mountain.
You got to release a weather balloon?
No, story problem. It reminds me of the high school physics.
Okay.
Guy jumps off a cliff and falls at such and such a rate and releases a balloon. All that garbage.
Yeah. Yep. Yeah. Let me see. No, I don't want that. Let's see if I can find it. Okay. Let's see. Who knows what the standard temperature is at sea level?
292.
Okay, that's the standard barometric pressure, but what's the standard temperature?
60 degrees.
In Celsius. I can't say yes or no to Fahrenheit because I have no idea. All I know.
I'm not just trying to guess.
You're probably right with the 60 degrees Fahrenheit, but I don't know what is 60 degrees Fahrenheit, and I can't do the equation. Like I said, I don't. Let's see what 60 degrees is.
I usually do I do a barometric pressure reading on fuel measurements every day, and then I always calculate how much the fuel weighs every day. So that's kind of how I said 60 degrees.
Pretty close.
Is it 15 degrees?
Yep.
Celsius?
Yep.
That's 59 Fahrenheit.
Yeah, 15 degrees Celsius. Yeah, really close. Like I said, I wasn't saying you were wrong. I just don't have any idea the equation to convert Fahrenheit to Celsius. I'll be the first one to admit that.
Yeah, I know. Getting so used to Fahrenheit, I have no clue what any temperature means in Celsius. So.
Yeah. Okay, here we go. Gosh, can we just narrow this down though?
Does anybody know how much Fahrenheit degrees is in 1 Celsius?
So the conversion is something like, to go from Fahrenheit to Celsius, as you take your degrees Fahrenheit, subtract 32 degrees. So say it's 59 degrees minus 30 degrees, and then multiply it by 5/9. And that gives you your temperature in Celsius. Let's see if I got it right. Just one. So we know 59 degrees is gosh. Wait, no. Let's see if I can work this calculator. So 27. Now we multiply that by 5. 15. I got it right. So I'll write that out really quick since I remembered for the first time in my life. So here's your equation to go from Celsius to Fahrenheit. So
You want us to write this down, or
you can if you want. Like I said, this is like the first time I've ever done it. You take your degrees Fahrenheit, you subtract 32 degrees, and then you multiply that by 5/9. There's your equation.
Do you want us to write that down, or?
You're more than welcome to. You're not going to be tested on it. It's just more for
Garrett, the way I grew up in my science classes, 5/9 is 55. So you can drop the second 5 and multiply it, and it's super fast. You can do it in your head. So you've got, say it's 62 degrees minus 32 is 32 times 5. So it just makes a
32 times 0.5.
Yeah, you can just drop the decimal and know it's not going to be, a factor of 10 off.
I'm going to test you. 59. Oops, minus 32 times 0.5. Oh man,
That's close.
It's close.
And then you can just take that second 5 and multiply it again. Anyway, it gets you darn close real quick.
Yeah. So let's see. I'm gonna try this again. Oops, 32. Times. Yeah.
There it is.
So as far as, do I put a jacket on or is it going to boil, or it gets you real darn close?
Yeah.
Yeah, that's a really quick, easy way to.
Yeah, so this, I think, when I did the 5 divided by 9, it's like 0.55555.
Right, so you can just go
and
up to
then
0.56.
like 9 at the very end. Something.
So in a good science class, you'll round up to 0.56.
Right.
So you multiply by 0.5 and then multiply by 0.6 and just add it to that first number, and you can get within a tenth. So
that's pretty good.
Then the other way, it's just 9/5. So you find that number and then do the same.
Right. Yeah, to go the other way would be your Fahrenheit, degrees Fahrenheit equals your degrees Celsius. I think it's divided by 9/5 plus 32. Something like that. Let's see. See if I got it right this time. So 15 divided by, oops, did it wrong already. 15 divided by 9/5 equals plus 32. Nope. Maybe it's multiplied.
Isn't it times 9/5?
Yeah, it probably is. That's probably where I went wrong. 15
If you
times.
divided by 9/5, you'd have to invert and multiply, it'd be 5/9 again. So I know it can't be that.
See, I suck at math. I have no idea what you just said. I'm going to trust you. There we go. That's it. Yeah. So take away that. Yeah.
It does. It's just remarkable to me. I mean, even in my earliest days in all my science classes, that they have not just standardized after all these years. Just about every science conversion there is has been metric and Celsius. I'm just stunned that we haven't kind of brought ourselves to standardize the world.
It's because we're American. It's not how we do it here in America.
Yeah, we don't standardize. They standardize.
Right.
Well, we do
we
believe
are
in the
the
metric
standard.
system. Well, Americans do believe in the metric system. Otherwise, there wouldn't be 100 pennies in a dollar.
That's right.
Yeah, some spots it's kind of like English. There's exceptions.
I feel like this is standardized, not the whole metric system and all that. I mean, that's just
Well, it's the
more
standard for
complicated.
us
I
here.
don't even know the metric system.
It's standard here in America, but it is not standard anywhere else. Everywhere else in the world, even like Canada, uses the metric system.
Not to mention in the U.S., if you're doing any science whatsoever, you will never see Fahrenheit.
Yeah, you'll see Kelvin, you'll see joules, you'll see Celsius. Like you'll see energy and stuff like that in metric form, not in a standard form.
I was not good at science, so
Yeah.
Because metric, all you're doing is moving a decimal place.
Yeah.
You don't have to do any calculations or conversions, and that's why it's far more efficient.
Yeah. But I don't know. Maybe.
But then you got me onto my pet peeve, so that's
okay. So we just had a little fun with. I honestly can't believe that I pulled that equation out because I have never used it. So
these number charts that you have pulled up, it sometimes irritates me. Like I can figure it out, but then at the same time, I don't know what it's talking about. Especially when I know that on the ADX they'll ask you questions of the numbers that are in between the numbers that aren't even shown on here. I have like no clue how to figure it out like that.
Yep. So that's the whole interpolate part, right? Okay. this is how we use standard adiabatic lapse rate. So in aviation, we have what we call ISA. Does anybody know what ISA means? It's in that video.
Is it something standard altitude?
Okay, so it's the international. Oh boy. One day I will be a pro at doing this, just so you guys know. Standard. Write this down. Atmosphere. Boom. There it is. So when we're talking about ISA, CJ, hit me with that sea level temperature again in Celsius.
It's 15 degrees Celsius and 59 Fahrenheit.
Okay. Let's throw away the Fahrenheit from here on out.
All right, 15 Celsius.
Okay, perfect. That's exactly it. Standard.
I'm not sure how to write the degree symbol on a computer.
It's like Control 248 or something like that. Are you on a Mac or a
Are you on
PC?
a Mac?
I'm on a Microsoft. Wait.
I don't know that on the Mac. It's Control Shift 8.
Yeah, on
You
a.
can Google it.
Here, I'll look it up for you really quick.
If I can't figure it out, I'll just put the word degrees.
No, I'll show you.
I think mine's a Windows.
Well, PC is your operating. You're PC based. How to do the degree sign. PC. Google's awesome. All right, so it's Alt 248. So hold down Alt and do 248.
Hold on. Let's see. Alt 248. Alt 248. Nope.
Are you holding down Alt?
Yep. Control 248.
No. Do you have the 10 key?
The 10 key, no.
On the right side. On the right side of your keyboard, it has the numbers.
Yeah.
Do 0176.
Nope. I'll just write it in words.
Okay.
It's not working.
You're good. Okay. So this is what you guys need to know. ISA stands for International Standard Atmosphere, and our standard temperature at sea level is 15 degrees. Okay. Super important. This you must memorize, especially What is the standard temperature at sea level?
15 degrees Celsius.
Perfect. Somebody else, what's the standard temperature at sea level? All right. You get the point. So, once again, standard temperature at sea level is 15 degrees Celsius. Okay. Let's look at what we call a winds aloft chart. This is where we're going to apply this ISA, the standard atmosphere, and we're going to use this 15 degrees Celsius. Now we're going to continue using this chart in our flight planning and stuff like this. So pay attention to here, and it'll make it easier when we start doing our flight planning. Okay, across the top, we have the key, okay? What this is telling us is this is giving us our altitude in feet above sea level. So at 3,000 feet, this column, that's your temperature, or your winds, your wind direction, wind speed, and temperature. At 6,000 feet, that's your temperature, wind direction, wind speed, and temperature. 9,000 feet, you guys get the point, right? Just separate these into columns. The government's too cheap to get Microsoft Excel for these. But hey, we make do with what we got.
I mean, those red lines are working perfectly, so.
There you go.
Okay. You would eliminate about half the jobs in government. You don't want to do that.
Yeah, that'd be bad. All right. I don't know if you guys...
Or you could make that a job. Just get someone to draw the lines in on everything.
There you go. I don't know if you guys know who Robert Kiyosaki is, but he does a book series called Rich Dad, Poor Dad, and one of his things that he always said that I still find hilarious, it doesn't really have anything to do with anything we're talking about, but he always said A students are employed by C students and B students work for the government. I just kind of think that's funny because I'm a C student. I don't have any employees, but yeah, B students all work for the government.
Teacher, this counts.
Well, I guess. No. But anyways, okay, so here we go. Here, if we go across here, this is giving us our winds, temperatures aloft at each one of these altitudes. Why do you think this first one doesn't have any information in it? Somebody just take a stab.
Is it just calm at that level?
What was that?
Is it just calm at that level? There's still.
So
it's because the airport is above 3,000 feet.
Yeah, perfect. There you go. The airport is at or above 3,000 feet, or it's so close to that 3,000 foot mark that the information would not be relevant. Does that make sense? So Albuquerque, I don't know the elevation of the airport, but it's somewhere in the 4,000 to 5,000 foot range, I think. So they just leave out that 6,000 foot because you can get your winds and temperatures at the surface off of a METAR, basically. Okay. But as you can see, once we get to an altitude at which the winds and temperatures aloft would be relevant, the information is populated. Okay. Let's just take, let's start out with a simple one. Let's start out right here in this box. You can see that there are four numbers, 2, 4, 4, 5, and then 12. There's also a minus there. Okay. You can break these numbers into pairs. Every winds aloft chart, you just break it off into pairs. Once again, you don't see the numbers here for temperature because you can just get that off of the information that's on your regular forecasts is relevant at those altitudes, so you won't see the temperature at the end.
So is that supposed to be a +2, or did I miss a column?
Where's that?
Oh, where you wrote 24/.
I'm sorry. Yeah, that's supposed to be a +2, +02. Nice catch.
Okay.
For some reason,
just trying to track, and then all of a sudden you messed me. I was thinking, wait, I don't get it.
My bad. I'm gonna erase all of this stuff so far. Okay. So right now we're talking about the winds and temperatures at 12,000 feet at ABI. Okay. So we break these off into pairs. And then a +02. Okay. So what this is telling us is the current wind direction. So it starts with wind direction. Write all this down. This is our wind speed. Okay. And then this is our temperature. Okay. So the way we read this is just like when we're reading runways. Wind direction is 240. Okay. The 0 is implied. Does that make sense to everybody?
Yes.
So let's say that you see wind direction is 0-1. What direction is the wind coming from?
010.
010.
Perfect. 10 degrees. Okay. Okay, wind speed 45 knots. We just read this number straight up. Okay. This is always going to be in knots.
And Garrett, just to confirm, is that 240 degrees starting from north, or?
Yeah. So when we're looking at winds, or really anything to do with aviation, everything's based on the compass rose. Okay, so north will always be referred to as 360 or 0. East will always be referred to as 090. South will always be referred to as 180. And then west will be referred to as 270. Okay, so 240, basically what's happening is that wind's coming from like a west-southwest direction. Does that make sense? And that means that the wind's blowing from that direction. So if we were to be standing here, the wind's coming from this direction.
Gotcha.
Okay. Now, just really quick while we're on this subject, I'm not trying to confuse anybody, but when we have a runway, say this is our runway here, is this side of the runway going to be 2-4 or is this side of the runway going to be 2-4?
I would say the southwest.
This side?
Yeah, the other side will be the other side.
This side? Okay, so this side, I'm just going to tell you guys that this side is the 2-4 side. The reason why is because we always land into the wind. We always want that headwind when we're landing. What the headwind does for us is it helps increase the lift, increase that speed of the air over the wing. Okay. So when we see a runway heading, that means that we're heading into the wind. So a 240 or a 24 on a runway, once again, just like everything else we're talking about right now, the 0 at the end is implied. With a 240 or a 24 runway, we would be heading into the wind at that point. So does everybody understand that principle?
Yes, and another way to look at it, I guess, is the way you could tell that 240 belongs on the opposite side of where the arrows you're drawing are pointed from is if you're facing that direction, you're facing west, which means you're facing 240.
Okay, yeah. So the wind is headed into your face, right? Headwind. Tailwind would be at your butt. So since we're talking about this runway as well, if we have a heading of, or this side is 240, this side of the runway is always the reciprocal of that number. So when we're talking, good, you can still see it. When we're talking directions, all we need to do to find out what this side of the runway would be, what the reciprocal is we subtract 180 degrees. That gives us 60 degrees. Okay. So this side of the runway, I'm not trying to throw too much at you guys, but this side of the runway would read, I wish I could just erase.
Runway 6.
Yeah, so it would be a 0.
Just say 06.
Yeah, it would just say 06 on this side of the runway. Does that make sense to everybody?
Yeah.
Yep.
Okay. And once again, the 0 on the end is implied. Okay. Okay. So we've got our wind direction, we've got our speed, and this is our temperature in what?
Celsius.
Celsius. Very good. Okay. So when we're reading this chart and how we apply ISA to it, is ISA the ISA lapse rate, or the standard adiabatic lapse rate is 2 degrees, and I need you guys to write this down, 2 degrees Celsius per 1,000 feet. Okay. So that means that at sea level, say this is 0, our standard temperature is 15 degrees, 0 feet. When we get to 1,000 feet here, what would our temperature be?
Negative
17 degrees.
Okay. So
sorry.
remember that the air gets cooler as we gain elevation. So I guess
13 degrees.
Yeah, so it'd be 13 degrees. Okay. We rise another 1,000 feet to 2,000 feet. We're down to 11 degrees. That's our standard temperature. Okay. Does that make sense to everybody, what we just did there?
Okay, so I got one question about so for different locations. So say like Las or say around this time it's 70 degrees in Vegas and 30 degrees somewhere else. So do you minus -2 degrees Celsius per 1,000 feet based off of the location of where you're at? Or
No. Nope. We're talking standard here. So we're going to talk about ISA deviation here and how the adiabatic lapse rate plays into our figures when we're getting our performance data. So you're jumping ahead a little bit. We'll get there, but this is what you guys really need to have a good understanding of. So for every 1,000 feet.
And what kind of lapse rate is that? I'm sorry.
This is our standard, just call it our standard lapse rate. So as the airplane's climbing from 0 to 1,000 feet, he should expect to see temperatures of 13 degrees. Does that mean that that's what it always is? Heck no. Rarely do we see temperatures that are standard at these altitudes. So let's take, for instance, St. George, or Salt Lake. I know Salt Lake better. So Salt Lake sits at about 4,200 feet. Okay. We'll round that down to 4,000 feet. What would be the temperature, the standard temperature at 4,000 feet? I'm going to make you guys figure it out the hard way, then we'll do it the easy math equation way.
$7 degrees.
Okay. So
can you tell me how you got 70 degrees? I'm kind of confused on how to figure it out.
Okay, so once again, we're losing 2 degrees per 1,000 feet. So what we're going to do to figure this out is we're going to take the first number here. So since it's 1,000, we're just going to take the first number. We're going to go 4 times 2. What does that equal? Right, 8. So that means that if we were to go from sea level to 4,000 feet, we would lose 8 degrees Celsius. What is our standard temperature at sea level?
$15 degrees Celsius.
Okay, 15 degrees minus 8 degrees equals 7 degrees Celsius. This is standard temperature in Salt Lake. Does that make sense, Matt?
Yeah, so you got the 7 based off of 7 degrees Celsius based off of the negative 15 degrees Celsius, or based off the 15 degrees Celsius, because that's your standard temperature atmosphere.
Not standard temperature atmosphere, that's our standard temperature. So you got to be careful. Okay. So once again, 15 degrees Celsius equals standard I need you to write it down just like this.
You're getting better. You're getting better and smaller.
Yeah.
It's standard temperature at sea level.
Right.
Sorry, no, my notes are partially covered, and where it's covered is the at part. So I automatically said atmosphere just by looking at the.
Oh, you're good.
That part.
You're good. So 15 degrees Celsius is our standard temperature at sea level. So when we go, if it makes it easier to just draw it out, draw it out. But it's going to get harder when we start talking about standard temperature at 39,000 feet. So it's 0 feet sea level, 15 degrees C, right? We go up 1,000 feet, 1,000 feet, we're at 13 degrees. We go up another 1,000 feet, it's 11 degrees.
So one more question about the 2 degrees for every 1,000 feet. Is it 2 degrees for every 1,000 feet or negative 2 degrees for every 1,000 feet?
So we lose. So I guess you could say minus 2 degrees. So for every 1,000 feet.
Depends on which direction you're going.
Right.
If you're starting at high elevation and then going down,
it
increases in temperature.
Right. So, so at 1,000 feet, or 1,000 feet equals, for every 1,000 feet, it equals 2 degrees Celsius, whether you're going up and down, up or down. If you're going up in altitude, then you're going to be subtracting. If you're coming down in altitude, you're going to be getting warmer. So to uncomplicate that, just remember that the air at the surface is going to be warmer than air at altitude. Your temperature decreases as you gain altitude. Does that make sense?
Okay, so yeah, so the way you got negative 8 degrees Celsius was just correct me if I'm wrong. So if the elevation at Salt Lake City is 4,000 feet, you times that by 2, you'd get 8 degrees, and since you're going up, it would be negative 8 degrees Celsius. And you take the standard temperature at sea level, 15 degrees Celsius minus negative 8.
Nope. If you minus to negative 8, that would be a positive 8, and you'd be adding it to temperature.
So
that's why I'm saying. Like you can look at my little scratch graph here. Okay. The way we do it is we're going to take the first number. Now I'm going to jump all the way up to 15,000 feet. Okay. 15,000 feet. Okay. We've got all these lines up to 15,000 feet, continuing this trend. So let's do 15,000 feet. We're going to take basically the first two numbers when we get above 10,000 feet, we're going to take those first two numbers. We're going to times that by 2. Okay. That equals 30, right? So now since we're going up, right? Since we're increasing in altitude to 15,000 feet, that means that we are losing 30 degrees Celsius. Okay. To figure out the deviation from ISA, to figure out what ISA is, what the standard temperature is at 15,000 feet, we would take negative 30 and we would go 15 degrees Celsius because we're going from sea level, and then we'd subtract 30 degrees Celsius to get our temperature at 15,000 feet, which equals a negative 15 degrees Celsius. Okay.
Garrett, I don't want to derail you, but in Salt Lake for about 3 months, that theory breaks down at lower altitudes with the inversion. How do they take account for that? Or do they?
We, as a dispatcher and for our flight planning purposes, we don't care.
Yeah, because, well, and that makes sense because at altitude, I mean, you're well out of that. You're way above the.
Yeah, so you got to remember we're talking standard lapse rate. Okay, when you start talking dry adiabatic lapse rate, or you start talking about saturated adiabatic lapse rates, or you start talking about pressure and density altitudes and things of that nature, then you can get more accurate with your temperature that is occurring currently. But when we talk standard, we're just talking like this is generalization. We're just getting our numbers as a general, like everybody across the board, this is how you get this number. So it really simplifies it for our flight planning. And it's the same way that everybody across the entire world does their flight planning. So as long as everything's standardized across the board, then we all get the same figures, right? But if we're sitting there trying to figure out like what's the standard and the adiabatic or the dry adiabatic versus the saturated versus, it just gets so muddled down and so confusing that, yeah, they know that pilots aren't smart enough to figure out all that stuff and get the same number. So
this really helps in my flight simulator because I've been trying to punch in all these numbers on my FMC and I can't figure out the temperature degrees at my cruising altitude, so I never know what to punch in on it.
Yeah. So when we're looking at this, we're looking to get our standard temperature at altitude. So now that we've kind of talked about this, I want you guys to send me a private message in chat. I want you guys to find out the standard temperature for 24,000 feet. When you get the answer, just send it to me in chat.
Sorry, Garrett. I can't type in the message for some reason.
You're fine. You're fine. Okay. Evan, walk me through it.
So, the way I did it, sorry.
You're fine.
So 24,000 feet, and you lose 2 feet every 1,000 feet. So I multiplied 24 by 2 and got 48, and I minused 48 from 15, and that comes out to negative 33.
Okay. So we took 24. Since we lose 2 degrees per 1,000 feet, we multiplied it by 2. Okay. That gives us 48. Okay. Since we're going up, it's getting colder, right? So 15 degrees Celsius is our standard at sea level. Oops. Man. So,
are we talking about the ISA diversion or just the ISA?
Nope, we're not talking about the deviation from ISA yet. We're trying to get ISA down first. So 15 minus 48, like you said, equals a negative 33 degrees. So standard temperature at 24,000 feet, negative 33 degrees. Okay, you guys want to do it again?
Sure.
That's not how cold it is in North Dakota right now.
How cold is it?
Cold.
How cold is it? Well, let's see. Usually around this time of year, it would be around like negative 20, but it's been a lot warmer for some reason. So let's see. Right now it is. Right. Oh, sorry. Right now it's 22 degrees.
Nice.
Fahrenheit. So I got to convert 22 into.
Oh, let's focus on this. Oh, that Fahrenheit conversion kills me. All right. So 39,000 feet. Everybody do that one really quick.
Want to convert though, right?
Yeah.
Okay, what'd you say, Garrett?
So everybody figure out the ISA at 39,000 feet. I want to make sure everybody understands how to do it.
Sorry, did you want us to just wait while we go over it or message you again?
Yeah, message me with the number. Sorry. All right, John, walk me through it.
Yeah, so it's the same steps that we've been doing. You take the first numbers of the 39,000, which is 39, times that by 2. You'll get 78.
Okay.
and you'll take 15 degrees Celsius minus 78. And that gets negative 63 degrees Celsius.
All right. Perfect. Take that, North Dakota. Yeah, so gets pretty cold up there, right?
Heck yeah.
Right.
That's
So it's just I'm gonna run through this one more time. So it's just the number times by 2, and then 15 minus that number equals our Celsius, right?
Right.
Okay. Just double checking.
Yeah, try working in North Dakota or 12 hours a day in the snow, blizzard, the cold, doing, fueling airlines in the cold is not so pleasant.
Yeah, I'm sure.
Especially when you have no.
Yeah.
Go ahead. I was going to say the address bar in Chrome also does an automatic conversion. If you type in negative 63 Celsius, it automatically spits out the Fahrenheit, by the way.
No way.
Yep.
I got to try this out.
They built a lot of things into that address bar that you don't know about. There's a ton of things like that.
So you're talking this up top here?
Yep, right in the address bar. Just type in negative 63 Celsius.
And then hit. Oh my gosh. Look at that. I'm completely blown away by it right now. You know that?
Pretty slick. They put a bunch of stuff in there. Like you type in a math problem, it automatically calculates the answer as you go. There's a lot of cool little things in that address.
That is freaking cool. That's kind of like I've learned some tricks at work lately about some. So first of all, I use a Mac at home, but at work, everything, like everybody's too cheap to buy Macs at work. So everything's always PC based. And yeah, PC, you click the roller bar, like on the refresh button, it'll duplicate and create a new tab and duplicate, the page that you're on. I was like, what the? How did I don't even scratch the surface with this stuff. And I thought I was tech savvy.
Yeah. I used to tech support 10 years ago, PCs, and so I was real comfortable with Windows. And then the company I've been with for 3 years is all Apple. So I'll tell you, Apple's hardware runs better, but Windows and in my opinion, Android on the phones have a lot better interface.
Yeah, it's a lot more customizable for sure.
That's it exactly.
But yeah, at the same time.
Just as a side note, negative 63C at altitude at 39,000 feet, just as an aside on jet engine performance, they're exclusively a heat engine, a heat differential. So it's very easy to see how they get such good performance at altitude, considering it's negative 63C, and then you throw some gas on it and burn it. It's a very big temperature change from front to back.
Oh yeah. Yeah, it's pretty amazing. What boggles my mind, since we're all aviation guys, geeks here, or else we wouldn't be taking this class, right? You look at World War II, and you look at the B-17 bombers and the different aircraft. Like the B-17 bombers, they flew at 25,000 feet when they were doing their missions, and it's all open air. You got the side gunners literally had a gun sticking out a window, and all of this is open. The entire center of the fuselage is open. So I can't even imagine how cold those guys got and wore those big old bomber jackets. But
I have a relative that was a tail gunner, and he has a picture of him turning around looking back into the aircraft, and his whole face was frosted over. His beard, his mustache, his stubble, he was just completely frosted over at altitude.
Yeah.
He said those superchargers, especially when they started putting all those superchargers, they'd get them up high enough, but it wasn't heated or they didn't have oxygen except, just the mask. And he said, man, you just freeze to death. Your toes would just get so cold and your face would get frost on it.
Yeah. I mean, I think about like the ball gunners, the ball turret gunners, those guys. Not only are they freezing to death up there, but their legs are elevated up above their chest too. So there's poor circulation going to their legs, and they're sitting in there for 10 hours. It just had to be miserable. Those guys were studs. So anyway, it's just kind of fun. But, okay. So we've talked about getting ISA. So when we look at this, let's go back to what we were, to kind of decoding this. Let's go 247340. Okay. So let's do a really quick. So anything that is, I think it's above 14,000 feet on these charts sometimes. Maybe it's 18,000 feet. Anything above this line here is assumed, no. I'm sorry. Anything above this line here is assumed to be negative. There's no way you can get a positive number above 24,000 feet. So that's why there's no negative or positive sign at these points. So that's why the numbers just kind of all mush. But it's the same exact principle, same exact concept. We break it into the 3 groups of 2. This is still our wind direction, wind speed, and our temperature. The only difference is we just assume that this is a negative temperature. Does that make sense? So our winds at this altitude, at 30,000 feet over this VOR, are 240 degrees at 73 knots. And it's minus 40 degrees C outside. Does everybody understand that? Oops.
Yeah, so you just change the temperature and you just change to a negative.
Yeah, like I said, anything at or above, that's what it is. Anything at or above 24,000 feet is assumed to be negative as far as the temperature reading. That's why up here you won't ever see a sign, is because it's just assumed to be negative. Does that make sense?
Yeah. So I forgot. I don't know. I didn't know this, but are we not talking about deviation, or are we going into?
We're going into that right now. So we needed to make sure that we understood how to get ISA, how to get that standard temperature at altitude. Now what we do is we do our ISA deviation, or how warm or cold the temperature actually occurring at altitude is in relative to the standard temperature. Okay, so the first thing that we do when we look at these charts is we look, first of all, at the altitude we're going to be flying. Okay, we're going to take this number here. like I had up here before, 247340. Okay, we break these down. 40 degrees is our temperature. We've got negative 40 degrees C at 30K feet. Okay, to figure out our ISA deviation, we first need to figure out what ISA is at 30,000 feet. So we go 30 times 2 equals 60, right? We assume that's negative. We go 15 minus 60. Okay, that gives us a standard temperature at 30,000 feet of negative 45 degrees. What is our current temperature at 30,000 feet? Negative 40 degrees. Okay, now we got to go back to the number line that we learned in elementary school. Okay. Okay, let's say this is a positive 45. This is a 0, and this is a negative 45. Oops. Okay, where would 40 lie on that number line? Right chair. Okay. So the closer we get to 0, that's a positive number, right? If we were to take negative 45 and add 5 to it, we would get negative 40, correct?
Correct.
Okay. That being said, our temperature, the way we would say this when we're talking ISA, is ISA plus 5 degrees Celsius. Does everybody understand that?
Hey Garrett, sorry, I almost got called into work, and so I got distracted a little bit because I was talking on the phone. So can you just backtrack a tiny bit?
Yep.
Thanks.
So we're going to go somewhere else now.
Garrett?
Yeah.
The fact that we were already given that negative 40 from this report, so where are we then listing it as ISA plus 5?
Okay. In our flight planning. So when we get into our flight planning, our performance charts are all based off of ISA. Okay.
Okay, gotcha.
So let me show you what a performance chart looks like. Course materials. Okay, so here's our performance charts. Maybe that's just our takeoff. Okay, should be right. Okay, yep. So here is our performance charts. Okay, as you can see, and we're going to get into this when we start flight planning. I'm just going to do a really basic overview. Our performance charts are going to be based off of, there's going to be one labeled climb, one labeled en route, and one labeled descent. Okay. So if we're trying to figure out our climb, we're going to figure out what our ISA is our average ISA is during the climb, and that's the chart that we're going to use. Okay. So the way this all comes together, and the reason why we're figuring out the standard the adiabatic lapse rate and the standard temperature at altitudes is because we're going to take that information, we're going to figure out the ISA deviation, the average ISA deviation over a certain segment of our flight, and then we're going to use that chart to derive our performance at that altitude. Okay, so this chart with that ISA plus 5, basically what would happen is if we were at 37,000 feet, okay, and we weighed 60,000 pounds, this is our performance numbers. Okay, and this first number is our time in minutes. This is the distance that we'll cover. This is our speed, our Mach speed. This is our rate of climb. This is talking our climb out, right? So it will take us 18.2 minutes to climb from whatever our airport altitude is to 37,000 feet. It'll take us 112 miles, 112 and a half miles. We'll be climbing at a rate of, we'll be climbing at a speed of 0.74 Mach, and that is equivalent to a rate of climb of 1,091 feet per minute. Our true airspeed will be 371 knots, and then the amount of fuel that we're burning per engine. This one's not per engine. During climb, the amount of fuel that we're burning during our climb, we will burn 1,849 pounds of fuel to climb to this altitude. So this is a chart that we're going to be using in our flight planning, but it's all derived off of our ISA deviation. You guys excited?
I am now, but like him, I could not figure out for the life of me how you got that 5. I'm like, I missed some math there. So.
Yeah, so we'll do another one here. Okay. So the first thing that we do is we're going to figure out our ISA, what is ISA at 34,000 feet. So do that equation that we just learned.
-53.
Okay. Our standard temperature at 34,000 feet is -53 degrees. Okay. So just hold on to this number here. We're going to go down to Scottsbluff. Here we go. Okay. This is the line that we're going to read from. At Scottsbluff, when we fly over Scottsbluff at 34,000 feet, this is what the winds and temperature are doing. Okay, so we've got 25, 69. Oh, I'm sorry, 96. And then 53. Okay, we're above 24,000 feet. What do we assume with our temperature?
Negative.
That it's negative. This one's super, super easy. Okay. So we figured out what the standard temperature is at altitude, and we figured out that when we cross over Scottsbluff at 34,000 feet, this is the temperature, right? Oops. Sorry, that's for Corey. Oh, you're talking about on this program? No. For some reason, it doesn't.
Yeah, so I don't get an undo.
Yeah.
Because there was something you were you were doing before, and I was about to screenshot it, and then you erased it all.
Oh man, I'm sorry. Yeah, if you guys ever see something that you want to screenshot or take note of, and I'm moving fast, tell me to stop, and I'll wait for you guys. Sorry about that. You'll probably have to.
We did another.
Yeah, we'll probably
have
to
one just like it. It's no problem.
Yeah, probably have to verbally tell me because I'm not too good at catching notes, as you guys have found out. So
that's why I'm on my computer. That way I can write things faster without having to write everything on my notebook, and then I'm just going to transfer everything afterwards.
Yep. So this one's pretty easy. So what is our ISA deviation at altitude?
-53.
No.
0?
0. We are at ISA at 34,000 feet when we cross over Scotts Bluff. Okay. When we're figuring out the deviation, we're figuring out the deviation, right? You're figuring out, I'm trying to figure out how to say this.
Well, I'm kind of confused because you said that the ISA is 0, but isn't it -53?
No. ISA is -53 degrees. ISA deviation is 0 degrees. We are 0 degrees deviated from ISA. At altitude, we're at -53. Hold on, just let me explain it. At altitude, we are at -53 degrees, and our ISA, our standard temperature at 34,000 feet, is 53 degrees. So we are not deviating from ISA. We are at standard temperature at 34,000 feet. Okay, we're going to do another one. Hold on. I know this is super confusing. That's why we're going to keep doing this and doing this and doing this. We haven't even got to the fun part where it tries to throw other numbers at you that aren't really on your compass rose. Okay. So let's go to 39,000 feet here. So this right here. Okay. This is what we're going for. We are at 39,000 feet when crossing over this VOR, ALS. I don't know what VOR that is, but we'll roll with it. What is ISA at 39,000 feet? What is our standard temperature at 39,000 feet?
-63.
Okay.
Is that ISA +4?
Nope. Or wait, yeah. So it's -63 degrees. Hold on, we'll get there. So standard temperature at 39,000 feet is -63 degrees C. Okay. This is standard. Once again, this is what everybody, if we use our adiabatic lapse rate of 2 degrees per 1,000 feet, this is what we get. Okay. -63 degrees. Now, when we're looking at the ISA deviation, we're going to take that -63 degrees. Okay. And we're going to add hold on. Positive, negative cancels it out. My bad. Ignore that. We're going to subtract a -59, which means that we're adding it, right? So subtract a -59 degrees. What does that give us? That gives us an ISA deviation of +4. Nope, I did that wrong. Son of a gun. Don't write that down. Bad.
Wouldn't you just say it warmed up 4 degrees, so that would mean it is a positive?
Yeah, that's a way of saying it. That's why I'm trying to refer to number lines from like elementary school. So here you have 15 degrees, a positive 15 degrees, right, on our number line. If we follow that number line down here, okay, here's our 0 degrees Celsius. Okay, let's say this is negative 15 degrees, negative 30 degrees, negative 45, negative 60, negative 75. Okay, now ISA, like we said, at 39,000 feet, so ISA at 39K equals negative 63 degrees. Okay, so we've got our negative 63 degrees right here. Okay, but the temperature that we have, or the actual outside air temperature, okay, is 59 degrees, negative 59 degrees. So are we moving in a positive direction or a negative direction on the number line?
Yeah, move.
Positive.
We're moving in a positive direction on the number line. So we're moving a positive 4 degrees. So when we write down our ISA deviation, we're writing ISA plus 4 degrees Celsius.
So I got a little confused there because didn't you say that the last two numbers of our temperature we would have to change that to a negative? Like you said that our temperature that's displayed on these charts, we would take that temperature and change it to a minus.
Yeah, so that's what I did here, right? Negative 59 degrees. So our current
Okay, so
hold on. So current OAT, outside air temperature, equals negative 59 degrees. Okay.
Okay.
Do you see that? Do you see where I'm getting that number? We're at 39,000 feet. This section right here is our temperature. And because we're above 24,000 feet, this temperature is assumed to be negative. Like we can just automatically go, no matter what, that's going to be a negative number. There's no way you can have a hotter temperature, a positive temperature at 39,000 feet. So we always assume that this temperature is negative. So that's what we did here is we're negative 59, and our standard, what it should be, according to our adiabatic lapse rate, would be negative 63 degrees. So we draw out our number line. Okay, here's our standard. And we draw out negative 63. Well, where's negative 59 in relative position on the number line?
It's only 4 numbers away. Okay.
Every time you move to the left on the number line, it's positive, right? If we're moving to the right, it's a negative. Okay. So since we're moving 4 numbers to the left, it's a positive 4 degrees. Okay. Now let's erase this number line. Does anybody need this
No, sir.
Okay. I'm going to draw this out again. Okay, let's say that we're at 39,000 feet and ISA at 39. Once again, is that right? Equals negative 63. We've already figured that out. Okay, let's just say, pretend that our current OAT equals negative 71 degrees. Okay, here's our 0. Okay, here's negative 63. Where is negative 71 in relative position to negative 63? To the right or the left?
To the right.
Yep. So negative 71 would be over here. How many numbers do we move to get to the 71?
8.
8. Are we moving to the right or to the left?
Right.
So when we move to the right, it's always negative.
Okay. Okay, that makes more sense.
Yep. Every time we move to the right on a number line, negative. Every time we move to the right, positive.
And that's how you always find your ISA deviation.
Yep, that is our ISA deviation.
It also makes sense. I mean, if you're getting if you're over a destination that's warmer, it's going to be positive number for ISA.
Yeah, so
yeah, that's how I think of it. If it got warmer, it increased.
Yep.
If it got colder, it's a decrease.
Yep.
If you're not a number line person, that's a good way to think of it.
Yeah. Yep. But you can't get confused though, because let's go back to these charts. Let me open them up again. Oh, hey, there we are. It's in your face and everything. Okay, let's look at what happens. Let's just take this very top right box, 66,000 pounds, 41,000 feet. Let's look at our fuel burn, okay? Our fuel burn is this top number right here in the corner. Okay. What do you think, since we've talked about pressure, altitude, density, like as you climb, like, and temperature, what it does to the performance of the engine? What do you think is going to happen when we go negative to a negative degrees? What do you think our fuel burn's going to do? Is it going to get less or more? Are we going to burn more fuel or less fuel?
Can you zoom that in a tiny bit?
As we get higher, is that what you're saying? And it gets colder?
Not higher, but warmer. We'll take the same altitude, the same weight, and we're going to compare the two. Okay, our current ISA deviation is positive 5 degrees, and we're burning 2,607 pounds in our climb.
I think the warmer it is, the more fuel you're going to use.
Yeah, exactly. Okay, so let's prove that out. Here, I'm going to write it down here so that we don't forget it. So, oops, not 9, but 7. 2607. Okay, now let's scroll up to the chart that is negative 5 degrees. ISA minus 5. There's not an ISA minus 5. Crap. Okay, let's do 10 degrees since I know there's a 10 degree and a negative 10 degree. That's really weird. I forgot about that. Okay. Once again, flight level 410. We're looking at ISA plus 10, and we weigh 66,000 pounds. Our fuel burn is 2682 at a positive 10 degrees. If we mix up those signs when we're doing our ISA calculation, let's see how big of a difference it is when we run our performance. Okay, here's our negative 10 degrees, and look at our fuel burn. What's the difference there? Let's see if I can pull up my calculator. No, I want it on top.
Kind of hard to follow because when you move, the circles go away or go to a different place. So I'm not.
Okay.
Is it like 200?
When you're zoomed in that much, I'm not sure we can see everything you're talking about.
Okay. So at positive 10 degrees, so this is at 10 degrees, ISA plus 10 degrees, ISA minus 10 degrees is 2415. Now I'm going to take it over and we're going to find out the difference that just 20 degrees of temperature swing makes. Basically forgetting or not getting the correct sign in front of our ISA deviation. Oops. No, that's not right. Okay, 267 pounds of fuel. Kind of important that we get that number right.
Okay.
Does that make sense to everybody? So let's go to a clear paper so I can write this out. Okay. Okay. So like I said before, when we were using the ISA plus 10 chart, our fuel burn to climb up to the 41,000 feet was 2682. Okay. Then when I did ISA minus 10 chart, my fuel to get to the 41,000 feet was 2,415 pounds. Okay, that's a difference of 200, what did my calculator say? 267. 267 pounds. You think that makes a difference?
I mean, like if you're 267 pounds.
If you're 267 pounds short of fuel, it's a pretty big difference, right?
Oh, yeah.
So
Sounds really bad.
267 pounds, just using our general calculation.
APU?
Well, the APU burns how many pounds?
260.
Yeah, 260 pounds per hour, right? But let's just use our normal engines. When we talk about the CRJ 700, basically the equation, so we burn about 3,000 pounds per hour, okay? But if we figure out how many pounds per minute that is, that equals 50 pounds per minute. So 50 times 50 or 50 times 5.
minutes.
Yeah, that's 5 minutes of fuel. You think that could make a difference? Could.
That's an approach.
Yeah. So
that'll also jack up if you messed up on that, that'd jack up your weight and balance too on landing.
yeah, good. The other thing is, just think that's just the climb. That's just your climb out. What if you're flying from Houston to Seattle and you mess up the signage on every one of your fuel calculations from Houston all the way into Seattle? That pound difference is going to be in the thousands of pounds. So it's pretty important that we make sure that we are applying the right sign to our ISA deviations. Does everybody feel good about it? So Matt, kind of what they were talking about, I just want to explain what they're talking about. Negative 71 degrees Celsius. Is that warmer or colder than negative 63 degrees Celsius?
Colder.
Yeah, it's colder. So it would be ISA minus, right? Colder always equals minus. If it's warmer, then it's a positive number. How do you guys feel about that?
Pretty good.
Good.
Yeah, there's a little bit of attention required.
Yeah, definitely. Huge attention to detail. And it only gets more and more that way.
It was the same with the weight and balance, the minus sign or plus or whatever. You mistranspose that and your whole calculation's jacked up.
Yep. For sure. I mean, it will completely change that CG. So I'm really debating. I don't really want to get too into this winds and temperatures aloft, but we've kind of hit it really good. And you guys have a pretty good understanding of how it works. So maybe we'll go into how to translate that. Okay. So everybody wrote down the wind direction, wind speed, and the temperature thing that I wrote down, right?
Correct. Oh, sorry, yes.
Okay, so nothing changes with this. The only thing that changes is that number on our compass rose. Do you guys remember what I said north was? The full circle?
360 or 0?
Yep, 360 degrees. So 750 a number on our compass rose? No. So what we do here is we go 75 before we add our 0 on the end here. Before we add our 0 on here, we're going to subtract 50 from this number. Okay, what is our new number?
25.
Okay, 25.
How did you get 50?
That's just the equation. Subtract 50 from that number every time. If you see a 7 or a number that doesn't make sense in front for the first two numbers here, subtract 50 from it. Okay, that gives us 25. We put our 0 on there. our winds are 25 degrees. Now, what do you think that does to our wind speed? We put a 1. So this is the way that this program that they use spits out a wind speed greater than 100 miles an hour. Is they add 50 onto our compass rose and take away the 1. So our wind speed and direction, 250 degrees at 104 knots. Did everybody see what I just did there? What happens to our temperature at 39,000 feet?
It changes to a negative.
We assume that it's a negative. So our temperature would be a negative 58. Okay, I want you guys to figure this one out. Right chair. Tell me what it is. In the chat.
I can't see the numbers. It's kind of far away.
Let's see here. Hold on. Let me pull it up here. Just 1 second.
Okay, so you want us to figure out the ISA and ISA deviation?
Nope. I want you to just translate that. I don't want you to figure out the ISA and ISA deviation. I just want you to translate it. Give me the raw data. All right, it looks like almost everybody has it. Okay, Greg, why don't you tell me what it is and how you got it?
I just took the 83 and subtracted off 50 because you've got a 0 there, so it gives you 33. Then you add your 0 for your, and then you add a 1 in front of the 00 for 100 knots.
Perfect. What's the temperature?
Sorry, minus 68.
Perfect. Does everybody understand that?
Yeah. Could also say calm wind if it's a 00.
Nope.
No? Okay.
Nope. Because why are we taking away 50? It's kind of like an addition, right? We're adding a 1. So we're carrying the 1 to the next section. So every time you see,
So if that's 37 or higher, then you know it's.
Yep. 37 or higher, you're carrying the 1 into the next group of numbers, which makes it 100 and something.
So if it's 36 or lower, then you would know the 00 is no wind.
Right. So, okay. So,
no, that's
good.
That's what I meant was the 00 means no wind. So
nope.
Wind
it doesn't mean that in this case.
That's it.
You've really got to, yeah. So you've got to really differentiate here. I'm going to show you what calm winds looks like, okay? When we are looking and we see a number greater than 37 or greater in this first two numbers, so 37 or greater, then we automatically assume that this speed, regardless of the number, if it's 17, if it's 00, it's a wind speed greater than 100 knots. Okay. In the event that it's calm winds, so think about this. If it's calm winds, there's no wind right now anywhere, what direction is that wind coming from?
I don't know.
Somebody said something.
North, 0 degrees.
Okay. It is coming from no direction.
There's no wind?
Yep, no wind. Wind's calm means no wind. So even if we take away our 50 from that, what do we come up with?
49.
Still not logical, right? On our compass rose, still not a logical wind direction. So if you ever see a 99 and a 00, that means wind's calm. I want you to write that down. Everybody. 9900 equals wind's calm.
Yeah, so I'm just having a little bit of a trouble understanding, like, so I know what you mean. So like 8300 and then 68. So you take 83 minus 50, you get 330 degrees. So 330 degrees. And then the part that I'm getting very confused on is when you say that we're always going to take those two numbers and like
put a 1 in front of it.
Always put a 1 in front of the two numbers?
Yep.
Always?
Yeah. So
okay.
That's exactly what I'm saying here. If you ever have an equation where you have to take, if it doesn't make sense on the compass rose, and you take away 50 and get a logical number for the compass rose, that means that it's a wind speed greater than 100 knots.
Okay.
And I think it'd be instructive, Garrett, to indicate what doesn't make sense means, because you may not understand that. So if you exceed 360, it's not on the compass rose.
Yep. So let's do one of those. So let's say for some weird reason that you had 911568. Okay. Subtract 50 from that. What do we get?
41.
41. Is that found on the compass rose? 410?
No.
No. Okay. That is greater than 360 degrees. Is it a 9900?
No.
Okay. So this, not logical, and therefore you would never see it on our graph. But if we look at, let's do 85 and then 99. Let's try a 99 here. And then 52. What does that break down to?
350 degrees at 199 knots, minus 52 degrees Celsius.
Perfect. Voila. Okay. Anytime that we have a number greater than the 360 on here, we subtract 50 and put the 1 into the next place. We know at that point that it's indicating that the speed is greater than 100 knots. So when we see this 199 knots, that's basically the highest this graph, this chart will ever report, period. Okay, they're never going to report a wind speed of 200. They're never going to report a wind speed of 300 knots, even though 200 plus knots is very probable at high altitude. They will never report anything above that 199 knots. So, does that make sense for everybody?
It does. The challenge with all these charts is they've condensed and boiled them down to such simple data that you lose the common sense to the numbers sometimes. The math doesn't really make sense because they've chopped out all the common sense to it.
Right. And really the hardest part for me was remembering. Like you said, there's all of these charts, right? Each one, you have to figure out how that chart functions, and it's really difficult. It is, at times, it's just downright brutal, because if you don't practice this and you don't look at these charts, let's say for even a month, are you going to be able to remember that? Probably not. I mean, you really kind of got to practice it and really drill it into your head that your winds aloft chart, that's how you decode those. So
from when I flew long ago, all of this is kind of a whole new thing to me, because the first thing you forget is everything we're doing. You never forget the flight. I mean, you'll never forget that, but all of this stuff, that's in one ear and out the other in a week. I mean, you don't remember any of this stuff.
Yeah. Yeah, it's a lot like riding a bike. You just got to get that refresher course, and then it'll come back. But you've really got to practice using these charts in order to really grasp them and figure out how they work. So we didn't get to turbulence today. I think I really didn't want to spend too much time on turbulence anyways, because I think that video really does a good job of covering the information in it. And so it'd be just me regurgitating exactly what's said in the video. Where the rubber meets the road and where we really start to understand what adiabatic lapse rates, and believe me, so I took an aviation meteorology class, and we talked about the Dowler and the Saller and how to calculate all of that. Do you think I remember any of that? Heck no. Do you think it was way too much information for me to retain and hold on to? Heck yeah. So applying it to what we actually use as a dispatcher, figuring out the standard lapse rate, and then figuring out how that computes to ISA, and then figuring out how that gives us our ISA deviation, that's practical, and that's exactly what you guys need to remember. So everything that we went over as far as that goes tonight, that's all information you've got to retain, and we're going to continue practicing all the way through the end of class. So are there any questions? If you guys are struggling with this at all, I highly recommend going through this video again, rewatching it on YouTube multiple times. If there's a certain principle that you're not fully understanding, and that way you guys will see, you guys can refresh that part of it. Does anybody have any questions?
No, sir.
Okay.
Jared, I do have a question, unless you're going to answer it already. I know that we've covered a lot of material and we're still going to cover quite a bit more. Do you have a guesstimation when we might take another quiz, just because I'm going to study this weekend?
Yeah, so yeah, we're going to do our quiz probably. I'm going to have to talk to Adam. I will give you a full day's notice. It will probably be Tuesday or Wednesday of next week. But
okay, I don't want to worry about it, or I'm just going to try. We've gone over it seems like we've gone over so many different topics, but
yeah,
I'll just review as best as I can.
So yeah, I mean, what I would really like you guys to focus your time on is this in-class video that we had tonight, the weight and balance, and then I want you guys to watch those weather videos that we've posted in your guys' folders for this last week. Rewatch those, get a good understanding, maybe even do some YouTube videos on top of those to help you understand certain principles. But the other stuff, we're going to do a pretty comprehensive review, just like we always do. The day before we take it, just take really good notes once again, and then we'll test you on it. We won't leave you guys hanging. So yeah, that was what I was going to bring up next. So that being said, are there any more questions or concerns?
No, just appreciate the info. This is good stuff.